In our previous session, we defined the function inside the transaction class to sign the input. And now we need to create the functionality where a user can send the bitcoins to somebody else. But before that, we need to take care of one thing. I have noticed that inside the account module, there is a minor typo mistake here. So let's fix that. It's public address. Change it to address and also fix this. And inside the data as well, since we have already added a couple of accounts. So go ahead and search for this keyword. You can do Control C and Control F. Type the copied keyword. Click on this drop down. Change it to address like this and click this button. So it will change everything public address everywhere. So save this file, close it, and now let's go ahead and define our new module, which would be send BTC. Send BTC.py. Create a class send BTC. Define the init function. This function takes arguments from account. So this means the account of the person who is transferring the Bitcoin, to account to whom you are transferring the Bitcoins, and amount, how many Bitcoins you are transferring, and UTXOs. UTXOs are unspent transactions. Miners keep track of all the unspent transactions. So when you request that you want to transfer money from your account to someone else, this is the place where miner will go and check if you have enough coins to transfer to someone else. So let's go ahead and define rest of the fields. And define one variable here, self.coin, and define the value of 100 million. This value is in Satoshis. So we need to convert all the Bitcoins into Satoshi. And then do self dot from public address. From public address equals to from account. Self dot to account equals to account. Self dot amount equals to amount. It's amount, not amount. So let's correct this into coins. So we are converting it into Satoshi. And last is self dot UTXOs equals to UTXOs. Save it. Now we need to define the function to create our transaction and sign the transaction. So let's go ahead and define the skeleton of our function. So define a function prepare transaction. So inside this function, we need to define a couple of other functions. So first one would be prepare transaction input, self dot prepare tx in, and the next one is self dot prepare tx out. We know these are the two main parts of the transaction input and transaction output. Let's save it and let's go ahead and define these functions. First, let's declare the function for transaction input. Self. Let's remove this part and add pass. Do the same thing for the transaction output. prepare tx out self and add pass here as well. So first, let's start with the transaction input. So for transaction input, first we need to define the list, empty list, txins, and then self dot total equals to 0. So how do we prepare the transaction input? In order to prepare the transaction input, we should already have some coins with us. That means we should have received the coins from somebody else in past, or in our case, since we are the miner, so we have the coins from our Coinbase transaction. So let's go ahead and understand that. Go inside the blockchain file, select all, convert it into JSON format. For example, this is the transaction we want to use, where we want to transfer, let's say, 10 Bitcoin to somebody else, and these 50 Bitcoins are locked to our public key hash. And one important point to note is the end user would not know what is their public key hash, so they will give their public address, which is this one. So once they will give their public address, at the backend, convert this public key address into public key hash, and then we need to find that what all coins are locked to you or the end user. So let's go ahead and define the functionality for that. So go inside sendBTC, close this file. So just now we saw our Bitcoins are not locked to our public address, but to the public key hash. So now we need to find a way to decode or convert our public key address into public key hash so that we can find out all the coins that are locked to our public key hash. So we already have the function defined for that. If you remember, decode 58 will do exactly same. So let's go ahead and import that function from blockchain dot backend dot util import decode base 58. Now let's go ahead and define the function to convert it. Define script public key. This will take the public address as input, public address, and then do decode base 58 and pass your public address, and it will give you your public key hash. That would be H160. Save it. And we need one more thing. Let's go ahead and import the script module from blockchain dot backend dot core dot script. Import script class. So what we will do is we will create the script public key because we will be using that in future when we are signing the transaction. So let's go ahead and prepare that as well. Public key equals to script and call e to public key hash, not inside but here, p to pkh script, and pass h168 and save it, and then return script public key. Now go inside the transaction input and add little documentation here. Convert public address into public hash to find tx outs that are locked to this hash. Save and do self dot script public key. Pass your address from, and then add this to another variable, self dot from address script public key. And one last thing, self dot from pub key hash equals to self dot from address dot cmds. Since we have prepared pay to public key hash, we know the H160 is stored at the second location, and we will use that to find the outputs that are logged to our public key hash. In the next step, we are going to define the functionality to find all the outputs that we are going to use as an input here. So go ahead and define new UTXOs empty dictionary and do try and do while length new UTXOs less than 1. I'll explain in a bit that what exactly we are doing here. New UTXOs equals to dict self dot UTXOs and then do time dot sleep 2 seconds accept exception as E and print the message error in converting the managed dictionary to normal dictionary. Let's fix all these errors here. First, let's import time. And this part as well. This should go underneath try. Save. So this UTXO is your managed dictionary, which means we have created or we will create a dictionary that is shared between processes. And here we are converting that dictionary into a normal dictionary because it has all the unspent transactions. And this is where we will check that which transaction belongs to which public key hash. So let's save it. And in the next step, go ahead and define the logic for TX byte in new UTXOs. Since it is in byte form, so that's the reason I'm using TX byte. If self dot total is less than self dot amount, then do TX object equals to, so we are reading it from dictionary, TX byte. And now we will run the for loop for index TX out in enumerate TX object dot TX underscore outs. If TX out dot script underscore public key dot cmds to equals to self dot from public key hash, the one that we have created in this step here. So we are checking it against the outputs that are logged to this public key hash. Then do self dot the total number of coins that we have in that transaction, TX out dot amount, and previous transaction hash, so which is TX object dot, we will do ID, so it will create your transaction ID, and that we need to convert it into bytes. So do bytes from X and pass this as a argument. Save. And in the final step, we will create the transaction input object and we will add it in the list that we created here. txins dot append txin. So we have the previous transaction hash that we are going to use as a transaction input, previous tx hash, and the index. Let's import transaction from blockchain dot backend dot core dot tx. Import transaction class, transaction in, tx out, and transaction class itself. All right. And what exactly we are doing here, for example, if you want to send 100 bitcoins, we have already seen that example. We want to send 100 bitcoins to somebody, but we do not have enough money in the one transaction. So we will combine multiple transactions. And this is exactly what we are doing here. If we want to send 100 bitcoins to somebody, and if that money is not enough, so we need to combine multiple outputs here. And that's exactly we are doing here. And when it has reached the 100 bitcoins, then we don't have to read further transactions, so we can simply break out of the loop. So add else and break. Also check if self dot total is less than self dot amount. So that means we do not have enough coins to send. So add the message is balance enough and add false here because we do not have enough balance to send. And finally, if there is no error, then simply return txins, which is our transaction input object. Yeah, this should be commands. So there is a typo right here. Change it to commands. And also the for loop should go inside the if statement. And now this is perfect. We have if, and if we have the total amount greater than the amount we are looking for, then it should break out of the loop. Perfect, save it. So in the next step, we are going to code our transaction output logic. So let's go ahead and define that. Define tx outs list, which is empty. Then self dot script to public key, self dot to account. So convert this account address into public key hash to script pub key. This is a script public key. So we are locking the coins to the specific person to whom we are sending. In fact, to his public key hash. And then tx outs dot append tx out object, which takes self dot amount comma to self script public key. So we are locking the coins here, and this is in caps. Save. Now let's calculate the fee. Calculate fee. So we need to pay to the miner to include our transaction in a block. So do self dot P equals to self.coin. So basically we are saying that we are paying 1 Bitcoin to add our transaction in a block. So 1 Bitcoin as a fee. Then do change amount equals to the total coins that we have here. So for example, we are trying to send 900 Bitcoins to somebody else, and by combining all the transactions, we have total 1000 Bitcoins. So which means we are just sending 900 to someone else. So rest of the 100 coins, we need to send it back to ourselves as a change. So let's calculate it. Self dot total coins we have minus self dot amount that we are sending minus self dot fee, which is 1 Bitcoin we are paying here. So rest of the coins should go back to us. Let's try to understand this with one more example. For example, you went to Starbucks, you purchased a hot chocolate, which is of $5, and you paid $10 to the shopkeeper. He gave or returned $5 back to you, and that is your change. And this is nothing different from that. You have total 1000 Bitcoins. You are sending 900 to someone else, and this fee can be considered as a service tax or the fee that we are paying to the miner, and the rest of the change will go back to yourself. I hope it is clear now. So let's create one more transaction output. UTXO dot append UTXO and define self dot change amount self dot from address script public key. So we are locking these coins back to ourselves. So if you look at this, we have two transaction output. The first one, the person whom we are sending, and the second transaction output is back to ourselves as a change amount. And finally, return UTXOuts object. So now we have our transaction input and transaction output method ready. So let's go ahead and prepare the transaction object itself. So let's add this to self.txins and this one to self.txouts. Save and prepare the transaction object self.tx object, which will take your version as an input, which is 1. Then self.transaction inputs object that we just created, self.txouts, and the log time. Save. And finally, we need to create a new function to sign our transaction. For now, we have just created the transaction. Now we need to sign the transaction. So let's define the new function. Define sign transaction self. So for that, what we need a private key, right? So let's go ahead and define a new function called get private key. So define it here. Get private key self. And first we need to import the account DB. So let's go ahead and import that from blockchain dot backend dot core dot database import account DB. Save it. Come back to our method get private key. Create all accounts variable and do account DB and read. So this will return us all the accounts that we have. Change this to this and save it. So the next step is read all the accounts and run a for loop. So do for account in all accounts if account public address is equals to self dot from public address, then return our private key. Private key. Let's quickly verify it. So inside the account file, we have the public address. This is the one that user will pass, and by using this address, it will return the corresponding private key, which is this one, private key and the public address. So variable names are matching public address and the private key. All right, so we have the private key now. So save this. So let's go back to our sign input function. So now call this and define a variable secret since it is our private key. Self dot get private key, and we need to import one more class which is private key, and that will be from the elliptic curve library from blockchain dot backend dot core dot elliptic curve import private key. Okay, go back to the sign transaction and do brief and the instance of our private key secret equals to the private key that we got from here. And finally, we will do from index input in enumerate and self dot tx ins. So if we have multiple inputs, so we need to sign each and every input, and that's what we are going to do here. Tx object dot sign input index your private key self dot from address script public key. So if we have multiple inputs, so first it will sign the first input, then second and third. So each input should have the script signature, and finally return true. Save it, call this function here, self dot sign transaction So our complete logic is dependent on the transaction input. And if you remember, we are returning this if we have the enough balance or not, just in case if somebody tries to send more coins than they own. So we should not run into issue. So we need to handle that situation. Also add self dot is balance enough equals to true by default. And if in case balance is not enough, it will set the flag to false. Save it. So let's go ahead and check if self dot is balance enough. If user has the enough balance, then only we should run all these steps. Otherwise, it should fail. So return true here. And if we do not have the enough balance, then it should return false. So we don't need to run the rest of the steps. And this return statement we will use when we will create the front end. So it will be helpful to display the error message just in case user is trying to send more coins than he owns. So we will display the message he does not have the enough balance or some kind of error message. And I think we have done pretty much everything to sign and create our transaction. So let's quickly recap it. So we have created this class. So user will pass the from account to account amount and the UTXO. So this is where all the unspent transactions will be. And then finally, we will prepare a transaction input and transaction output. And once we have the transaction input and transaction output, we will sign the transaction. And that's pretty much we are doing in this class.